Ever wanted to create a game and have to set up the weight and gravity? Never? Me, yes, on game projects. But well, we shall now realize one that renders bouncing spheres on our screen with real physics calculations. It is very simple. Then we can modulate it to other projects and have a better visualization of gravity laws and applications. We shall use Rust. Why? Well, there are Python, C++, well, a bit not easy. But Rust? Excellent question. He's very efficient and memory management adaptable. For example, it is used in games like Tiny Glade, Valoran, or even Flamegrower. Pretty good, right? Hey, before we get started, let us remind some things in Rust. We manage motions by frames, like we separate each part of the motion by small clusters of time. We precede the Grand Design ECS, the Entity Component System pattern, which will be handling the chaos of the motions into very organized spreadsheets. Yes, for real, we have something who manage it for us. Before we start the coding, we need dependencies like Macroquad to create window, render, input, as for the game loop. Then Glam Vec2 to handle 2D vector math for positions and velocities. Now, we're ready. ECS separates what things are, the components, from what acts on them, which are called systems. Sounds fishy, right? Guess there is still OOP to do so, but it will be useful, I assure. In our simulator, we need entities, but in Rust, and in our case, we just need usize index, an ID with no data of its own. There are no objects stored, no unused space in our program. As for all the structures created in this project, we make a copy. Why? Because if you try using a variable, it will be deleted. It's where Rust revealed to be very wary of space management. Now, you must see me weird. Why chose this shitty language? But Rust is very good to create performant app just because of this very rudeness. Then, we need to know where the entities are in the world space, with position, the speed and direction per frame with a velocity, the physical mass with a mass, and the collisions with a collider. Now, we have something. World holds one vec option T per component type to store them all out. Each index corresponds to an entity. None will designate an entity without a component. A simple sparse set substitute.
Each system is a plain function taking mute world and dt, smallest amount of time where time matters. They iterate over all entities and act only on those with the required components. That only make Rust performant for games, don't you think? Here, the modifications applies to all the components. We won't need to iterate over each element. Paradise, right? We need to every velocity that also has a mass. Mass acts purely as a presence flag. Here, we use gravity_system to add 0,500 times dt. The components must move in our world. For that, we use classic Euler integration in a movement system. There are pretty much components. We shall manage the collisions in a collision system, like here, which will detect all overlapping pairs, store then push entities apart by half the overlap each, then swap velocities, dampened by 0.8. Velocities are copied out as plain vec2 values before writing back, avoiding a double ampersand mute on the same vec, which can cause some errors. What to do if the components collide with the ground? We let them explode? Nah, they bounce in predefined directions with a ground collision system like this. Not only the ground, if the component hits the wall also, they won't pass through, but collide. We let wall collision system manage it like here. And finally, we draw and render this all with a render system, like here, who takes the world, immutable, draws a gray ground line, a dark arena border, then for each entity with a position and collider, a translucent blue-filled circle plus white outline. Now all our project and reactions are set it up, we need to launch them all. In this part, the 33 millisecond cap prevents the simulation from blowing up if the window is minimized or the CPU spikes though. Now, a mini recap. We used the option T pattern per component, which sparse components without a real sparse set. The two-phase collision, with collision system that avoids simultaneous mute on the same vector. The copy principle on all components or structs that lets you read a value and then mutably borrow the vector again. We could have also done naive physics like update and check, but what if spheres pass through each other? We needed continuous collision detection. Then we wanted to disturb our peace and used an immediate mode. No ECS. It will give spaghetti code incoming. While I like spaghetti pretty much, our approach here is rather maintainable. It's why I recommend ECS method. You can create your own project using this steps. We create and set up the project typing this in your terminal. We need to add dependencies in a .toml file. We implement the ECS. We create world struct with component vectors, implement collision detection. P.S. the hardest part. Create rendering system. Easiest part. Macroquad is magic. The gravity, velocity equals gravity times dt. Movement, position equals velocity times dt. Collisions, detect plus resolve. Boundaries, keep spheres in bounds. And run and enjoy with.
We can pass through all that, or just ask AI to generate it with this prompt here. Don't worry, it's in the description with the Git code link. Have a happy physics coding. And remember, if the compiler doesn't complain, it probably works. I recommend to ask the AI to act as a mentor if you really want to understand and be able to upgrade it yourself. To finish, I prioritize visualization over just code to code, because we don't code in the black. We code something that matters, or just to pass time, but it's still real in our head. A code is just our way and language to make it come to reality. That's what I wanted to say. Then, thank you for your attention and support. Subscribe, please, if you liked, and see you next time for a new project.